Okay, we're going to look at some other features of functions. And the first one we're going to look at is what we call symmetry, because some functions have symmetry really in two ways with respect to the x-axis. Actually, I should say that again, the y-axis. If it was x-axis, then it wouldn't be a function, would it? Okay. So some functions have symmetry with respect to the y-axis. One such function that we have here as an example would be y equals x squared, or f of x equals x squared. Okay, anything that's on the right, xy, is going to have a corresponding negative x, positive y coordinate. Okay, and so ultimately the symmetry here is with respect to the y-axis. Okay, if that's the case, if we have a function that is symmetric to the y-axis, we call that an even function. So an even function, okay, again, graphically, is symmetric to the y-axis. Now, algebraically, okay, this right here is a fact. I'm going to show you how to show that in just a minute. Okay, and with that said, if I look at my function f of x equals x squared, okay, what I want to do to show algebraically that it's even is to take a look at f of negative x. Okay, I know f of x is x squared. If I were to put in a negative x instead, okay, and then simplify it, if I do negative x and I square it, what would that give me? It'd give me x squared. Okay, no matter what I put, if I put a 5 in here and squared it, and I put a negative 5 in here and squared it, wouldn't I get the same answer back? No matter what? Okay, and so this is the algebraic proof that this is an even function. If I can put a negative x into the function and get the exact same thing back that I started with, then we consider that an even function. If I were to graph it, it would have symmetry over the y-axis. And also, if you look at the table of values, the numerical approach, we can tell that this is symmetric because okay, opposite x values give us the same what? Same y values. Okay, so opposite x's give us the same y's. Right? Now, if I have a non-function, okay, as I mentioned the first time, which I meant y, but this time if I have symmetry with respect to the x-axis, okay, the first thing we want to note here is that this function that I have drawn here, this sideways parabola, is not a function. Okay, I just called it that, but really, is that true? No. It's a relation, remember, it's a set of points, okay, but it is not a function. However, we could still graph it, okay, and we'll spend a little bit more time on non-function graphs later, but ultimately it doesn't pass the horizontal line test, as we mentioned, but it does have symmetry with respect to the x-axis. Okay? All right, so any y-coordinates that are opposites are going to have the same x-coordinate, if you will. Okay? Now, when we have a function like x cubed, okay, if we look at the graph, we can see that this function is symmetric about the origin, okay, or symmetric with respect to the origin. Okay, and you think about it from geometry too, it's really essentially just a turn of 180 degrees. If we were to take this branch and turn it 180 degrees, we'd be on this branch then, wouldn't we? Okay, so it's like a rotation as well. Anytime we're symmetric about the origin, okay, it's essentially like a rotation of 180 degrees. Okay, now notice also that if I have any xy point in this situation, okay, there's going to be a corresponding point that's negative x, negative y. So any point in the first quadrant, there should be a corresponding point in the third quadrant. Okay, could it also be reversed where I have something that goes from the second quadrant into the fourth quadrant? Sure. Okay, that could be odd also. Okay, and that's exactly what that kind of function is. It's an odd function. And algebraically, the key is if we plug in negative x to our function, we get the opposite of what we started with. So in this particular case, if we wanted to prove it for x cubed, we would put in negative x. And if we simplified that, it'd be negative x times negative x times negative x, which is negative x cubed. And again, aren't the two results opposites? And notice what do we have up here? Opposites. Okay? F of negative x is equal to the opposite of f of x. Okay? So if that's the case algebraically, then we have a odd function. It's symmetric about the origin, and numerically, any opposite x's are going to produce what kind of y's? Opposite y's. Okay. Now, there is a generalization for here too for odd functions when we're given power functions. Anything that's x to the n, notice it says, okay, anytime that n is odd, it's going to be an odd function. Okay. Think there's a corresponding rule for even powers? Definitely. Okay, if it's an x to the 4th or x to the 6th, okay, we're going to raise that to an even power. We're going to get back to x to the whatever. It's going to be positive, so it's going to be the same with even functions, okay, in terms of even and odd powers. Okay. Now, let's take a look at this one. This one says, is f of x, tell whether it's odd, even, or neither. Now, keep in mind that we could look at a table, we could look at a graph, and decide about the symmetry, and decide whether the opposite points give us either same or opposites. Okay? But if we're going to show it algebraically, again, what we want to do is we're going to put a negative x into the function and see what happens. Okay? All right? If we put a negative x into the function and then simplify, we get x squared plus 3. So how does that compare to what we had at the beginning when we had f of x? It's the same. So what have we just proven? That this is an even function. Okay. How about this one though? What if I told you f of x was 2x squared plus 2x plus 5? Okay. If I were to put negative x into it, I would get 2x squared minus 2x plus 5. So how does this compare to what I started with? It's not the same, so therefore it's not even. Now my other question though, is it exactly the opposite of what we started with? Okay, keep in mind we need to know what would the opposite of this look like. If I wanted the opposite of this, it would have to be negative, negative, negative. All the signs would have to be opposite, wouldn't they? Okay? And so since it's not that either, then the question in this case would be it's what? It's neither. Okay? So it's not even because it's not exactly the same. It's not odd because it's not exactly the opposite of what we started with. So therefore the only choice is what? Neither. So every function we deal with is either one of those three, isn't it? It's either odd or even or neither. Okay. Now, we're going to finish up talking about horizontal and vertical asymptotes. Okay, we've seen quite a few of those in what we've done so far. Okay. But ultimately, we're going to look at a couple definitions first, and then we're going to look at an example or two in just a minute. But ultimately, when we have a horizontal asymptote, okay, it's some line y equals b, so b could be whatever number. Okay, that is going to be what we call a horizontal asymptote if f of x approaches a limit of b as x approaches infinity or negative infinity. Now, here's this limit notation, and this is a very important part to what we're going to be dealing with here today. Okay. When I write this sentence, which ultimately is read as, in either one of these, it's the limit as x approaches infinity, or the limit as x approaches negative infinity, of f of x is equal to b. Okay, so the limit as x approaches infinity of f of x equals b. And what that really means is this. Okay, a few minutes ago, we had a problem that looked like this, graph-wise, right? True? Okay, and we determined that no matter how far we go out on this branch, okay, the maximum it's going to get up to is -1. True? So that means that if I were to draw it in there, in my little drawing here, okay, that -1 line at y equals -1 is what we call a horizontal asymptote. Okay? So in our particular case, we'd have y equals -1 as a horizontal asymptote, because as we approach infinity in the x direction, okay, what are the y coordinates like? The y coordinates are getting infinitely close to, guess what? -1. Okay? So these two things essentially go hand in hand. That the fact that y equals 1 is a horizontal asymptote, okay, goes hand in hand with the fact that the limit of this function as x approaches infinity of f of x is equal to 1. Okay, -1 I should say, sorry. So if we have a horizontal asymptote, okay, then that limit statement is going to be the exact same answer. Okay, and all that limit is saying is that as we get bigger, as x gets infinitely big, okay, the y coordinates, which is f of x, are going to be close to -1. Now, do we actually have to get to -1? No. Okay, they're just going to get infinitely close. And ultimately, on the other side, we could say the limit as x approaches negative infinity of f of x, okay, that equals also -1 in this particular case, because as we go off to the left here, okay, as we go infinitely far to the left, okay, then what's going on with our y coordinates? The y coordinates are getting infinitely close to also what? negative 1. Now, one thing we have to be careful, and we're going to spend a lot of time on functions that have these features, okay? So we're just kind of looking at some definitions today and seeing what it might look like. But one thing to think about is that for all functions, okay, if it behaves a certain way going off to the right, it doesn't necessarily behave the same way going to the left, okay? So with that said, could there be two different horizontal asymptotes maybe? Sure. Or could there be just one going right and none going left, or vice versa? Sure. Like I said, we're going to see some functions that have some different behavior, but ultimately we just need to recognize that if this is doing that it's a horizontal asymptote. Okay? All right, and they always have to do with behavior at infinity or negative infinity, and that's the key. Okay? Now, remember though, with this function we also had vertical asymptotes, and we had some stuff going on in the middle here. It went down to 3/4 if you remember. Okay? All right, so with that said, the behavior around a vertical asymptote is going to be as follows. Okay? Our vertical asymptotes in this case, if I remember right, they were -2 and +2. Those were our vertical asymptotes. And again, they're equations for lines, so you can't just write the numbers. They need to be equations. So x equals -2, x equals 2. Okay, what we'd write for limit statements for these to describe what's going on is we'd write this. We'd write the limit as x approaches -2, and then we put a little minus sign up there. That means from the left. Okay. And let's look at our picture to see what the answer is. Here's the left over here. As we approach -2 from the left, what's going on with our y-coordinates? What are they doing? They're getting infinitely small, so therefore the answer to this limit would be -infinity. Okay, and that means that it's going down as we approach that asymptote from the left. If we have x approaches -2 with a plus sign, that means from the right. Okay, from the right, that's over here in this area. And what's going on with my y-coordinates as they get close to -2 from the right? They're getting what? They're getting bigger. So therefore, that answer would be infinity. And any time that one or both of these are either infinity or negative infinity, okay, it's an asymptote. Okay? That's what kind of behavior you have if either one of those are infinity. And if we finished with x approaches 2 from the left, x approaches 2 from the right, okay, as I approach 2 from the left, these are getting what? They're getting bigger. So from the left, this time that one's infinity. And from the right, which is over here, as I approach from the right, these numbers are getting what? Infinitely small, so that one would be negative infinity. Okay? All right. Questions so far? All right, so let's take a look at this graph right here. It says identifying the asymptotes. Okay? When we have asymptotes, they are going to occur when the bottom equals 0 here. If we're lucky, this will factor. Like in this particular case, it factors. Okay? So we should expect that we have asymptotes where we have these discontinuities, where we have the parts of our domain that do not work at 2 and -1. Okay? So we would say x equals 2 or x equals -1. Those are going to be where our two asymptotes are. And could we verify that by drawing the graph? Certainly. Okay. Now, there's one other issue. Oops, before I do asymptotes. Okay, there are two vertical asymptotes here. The other thing that is going to be a fact is that in some cases there's going to be a horizontal asymptote, as we've seen. If we were to graph this, we do x divided by x squared minus x minus 2, and we look at the graph of it. Okay, how about horizontal asymptote? What does it look like as we go off to infinity and negative infinity? It looks like it gets really close to the what? Yeah, it looks like it's close to the x-axis, doesn't it? So in terms of horizontal ones, okay, our conjecture here would be that it's y equals 0. We could check with our table as well, pick some big numbers of x and see if it actually is really close to 0. True, it is in this case. We're going to talk a little bit more later about how we can tell from the equation that there's a horizontal asymptote as well. Okay. For the time being, we'll leave it at just looking at the graph and using our graph and table. Okay. There is something about this function that, you know, if I looked at it, I would know that there's a horizontal asymptote at 0 just because I know something about this function. Okay. So we're going to study that a little bit later on too. Okay. All right. So that said, your